So we moved into this chapter entitled Reacting Mixtures and Combustion. Combustion. What is combustion? Well, it's a particular reaction. Just like what it sounds, you have a fuel, and typically a hydrocarbon fuel. So a hydrocarbon fuel has a hydrogen and carbon and some mix, A, coefficient B on those in some molecule. You get it under right conditions in the presence of oxygen, which is our, it doesn't have to be the only oxidizer, but let's just, for this class, oxygen is our oxidizer, and it combusts, and when we have a reaction, the carbon goes to CO2, that's where the carbon goes, and where does the hydrogen go? The hydrogen goes to H2O. And depending on the coefficient A for how many carbons are in that hydrocarbon fuel, depends how many CO2s you get. And the coefficient B for how many hydrogens are in the hydrocarbon fuel depends on, will dictate how many water H2Os you get. Well, once we have a review of chemistry and combustion, we'll want to apply the first law, conservation of energy, to reacting systems. We can then compute things like, very interesting, the adiabatic flame temperature. I combust it perfectly. What is my flame temperature if there's no heat transfer to the surroundings? And then the other is, after we do the first law, we want to do the second law. Well, to do the second law, we have to talk about how to calculate entropy for these systems. And you get basically the third law of thermodynamics. One person one time asked me, do you ever cover the third law of thermodynamics in Thermo 2? Yeah, we do, but it's very briefly. It's not like I spend a week on it. And it's just a concept. I mean, did we have the first law of thermodynamics? Yes. What was it? It was about the conservation of energy. Second law of thermodynamics, about energy has different forms, and there's some, it's difficult to convert some forms of energy into other forms, and it's really easy to go the other way. So it's like there's a different quality to energy. Some energy is very valuable. It's a high quality. And some energy, it's energy, but it's a lower quality. And so it's hard to convert from a low quality to high quality energy, from a heat transfer to a work transfer. That's really hard. From internal energy to potential or kinetic energy. That's pretty hard. But it's easy to convert the other way. From potential energy and kinetic energy into internal energy, easy. Or you think about burning something, turning something like through friction and dissipating all that mechanical energy into just heat. That's easy. Well, that was our second law of thermodynamics. There's limitations on the transfer of energy between forms. That's pretty hard to describe, isn't it? But it's a limit on energy transfer. The third law, we're going to get to, hopefully today, basically talks about absolute entropy and having a common scale for entropy calculations. And basically the third law says something like the absolute entropy is 0 for a pure crystalline substance at 0 Kelvin. Pretty abstract. But it's like no wiggle room on the molecular level. Everything's fixed and stationary. Well, when you write a reaction equation, it can be reversible or irreversible. A lot of these reaction equations are for combustion are irreversible, hence we draw one arrow instead of two. But we'll have reactants and then products, R's and P's. And what are on the reactants? A lot of times our fuel, our CH4 would be a good fuel, methane, and some oxygen. What would be the products? CO2 and H2O. So our combustion is our fuel plus oxidizer goes to products. What are some fuels? You're going to use them a lot, but if you haven't memorized them already, just sit them down and memorize them. What is methane? CH4. What is propane? C3H8. And what is octane? C8H18. So Methane, why do we study methane? Because there's a lot of it. They're making a lot of people rich in America again, right? With drilling and fracking primarily to generate lots of methane in wells and that. So that's natural gas. What about propane? Well, it's a more valuable gas. You use it in a lot of different places. It's a C3H8. You can buy it in almost any hardware and a lot of other stores. They sell it in little bottles. If you take those bottles and slosh it around, you can see that at that pressure and temperature, it's in the liquid state inside that bottle. When it's empty, a lot lighter. So it's very ubiquitous. And how many people have propane gas grills, right? That's what they're burning. Then octane, what does that sound like? A little bit like gasoline. And that would be, I know that gasoline is a big blend of a lot of things. And if you could isolate it down to octane, which nobody does, then that would be like the benchmark 100 octane gasoline. So it's kind of a way of representing gasoline in a very quick way. Is C8H18. Now the products, every one of these C's, every one of those C's in the hydrocarbon, when it completely combusts, goes to CO2. How come, Professor, it doesn't go to C2O4? How come it doesn't go to C8O16? I don't know. It's all on chemistry and how these molecules are happy. It's the happiest state. It likes to go to CO2. It's like lowest energy state. And so, other than that, how come it can't go to C1.5O3.2? Don't do that, right? We just leave that all alone. Go talk to your chemistry instructors. Carbon goes to CO2. How come it doesn't go to CO? Well, first of all, we like to breathe, or it's okay to breathe CO2. It can give us a headache in high concentrations, but it won't cause us to become asphyxiated, right? Basically, CO is carbon monoxide, and when that gets in, it clogs up your lungs such that you can't get the oxygen you need and you die. So CO, carbon monoxide, is really bad. Carbon dioxide, actually everybody in here in this room is exhaling, and when you exhale, you are throwing out into the room CO2, carbon dioxide. So is this the one which their global warming concerns? Yeah, that's CO2. A few years ago, nobody really gave it much thought for how much emission of CO2 there is. They worried about hydrocarbon emission out the tailpipe of cars, as well as carbon monoxide out the tailpipes of cars. Put on catalytic converters and other things to help reduce emissions from automobiles, and there you go, we're happy. Hydrogen goes in this fuel, see all the H's, they go to water. How come it doesn't go to something else? It just doesn't, okay? It's happy and water energy state. Okay. What's that funny joke, right? When people learn what water is in chemistry, here's a quick joke. It's a high school joke, if not even lower. Probably half of you know it. So the person goes into the restaurant and the person says, "What would you like to drink?" "I'd like some H2O. The waiter knows he's asking for water. I'll bring him some water. So he asks the other person at the table, "What would you like to drink?" "I'd like some H2O too." So he brings them some H2O2. They both take a drink and one dies. And what is the H2O? H2O2? Hydrogen peroxide. So it's not much different than H2O, but it's dramatically different when you interact with it. It's just like, what's the difference between CO2 and CO? One is very deadly and one is fairly benign, right? You can get into a room and be typically outside in the air, maybe it's about 400 ppm CO2. In this room right now, I'd say start of the day, 8 o'clock, 600 ppm, 500 ppm. You've been breathing. The air conditioning system in some rooms, they don't work too well, don't have a lot of fresh air coming in. It could get up 800, 900, 1,000, 1,200 ppm. Easy, and you don't really sense it. It starts to get 1,500, you start to feel like it's kind of stuffy in there. It doesn't feel good. It's 2,000, some people are very sensitive. 3,000, they may get ppm, they may start to get a little, like, I don't feel good. I get a little nauseous headache. Some other people, 5,000, they don't care. They don't feel it. But CO2 is not a killer. So where do we get the oxygen from, if that's our oxidizer? Well, you can buy pure oxygen, and if you're interested in getting a very high adiabatic flame temperature and trying to melt something, you would typically get oxygen out of a bottle with your fuel. But when we're running an automobile and we're burning gasoline in our engines, we don't have bottles of pure oxygen. It's very, very expensive. So we get oxygen primarily from air. We ingest air to get the oxygen to combust the fuel, to burn something. Where else? If you're NASA and you want to send some rocket out, you want to get some oxygen from pure oxygen. It's a great source. You don't have that troublesome nitrogen with it. When you bring in air, you're bringing in, 80% nitrogen, and to get the 20% oxygen. So, but this really costs a lot of money if you really want to burn a lot of oxygen and you want a pure source O2. Well, when we have our reaction equation, we have stoichiometric coefficients. These are those coefficients that are in front of each of the entities in our balanced reaction equation. So let's start off and let's do it with CH4. I forgot. What is CH4? Methane. Why do we care about methane? Natural gas. Natural gas. All right. And we're going to get the oxygen from air. Now, if we get the oxygen from air, and the oxygen is, the standard air is 21%, so 1 kilomole of air brings in 0.21 kilomoles of oxygen and about 79 kilomole of nitrogen. We're going to just consider air as being either nitrogen or oxygen. And it's 21% is oxygen and the rest is nitrogen. We just lump the rest. The argon, the CO2, the water vapor, everything we can just lump in there. If that's true, and I want to bring in 1 kilomole of O2, how many kilomoles of N2 do I need to bring in? See, this equation I just take and I multiply by 1 over 0.21. So what is 0.79, if you have your calculator? 0.79 divided by 0.21. 3.76. Now, Professor, I see 3.7619. Round it off. Okay? Because this is just rough, okay? So let's do this. If I want to get 1 kilomole of oxygen, I now know that I need 3.76 kilomoles of nitrogen tagging along, but how many kilomoles of air did I ingest into the whole system? How many kilomoles of air do I ingest in the whole system? It's 4.76 kilomoles. Right here, I'm going to tell you, on the final exam, there'll be some students who'll make an error. This is the source of the error. They forget what? To bring in 1 kilomole of oxygen from air, I have to bring in the tag along 3.76 kilomoles of nitrogen, meaning a total of 4.76 kilomoles of air have been ingested. True or false? Remember that. How many times I've graded final exams and I'll just, don't forget this. Hey, did I say something important? Hey, last year I graded final exams. Even though I said it 5 times, students made this error. Guess what? They lost a lot of points. Do you want to do that? Remember this. Okay? Oh, they just forget it. I'll show you where they forget it. So now, I'm going to bring in 1 kilomole of oxygen and 3.76 kilomoles of N2 in that right ratio, and now basically I'm going to figure out what that stoichiometric coefficient is in front of the 1 O2 plus 3.76 N2. Okay. That goes to CO2, and I don't know how many carbon dioxides yet. We're going to balance it. And it goes to H2O, and I don't know how many H2Os it balances. I have put some coefficient I'm going to solve for. And then it goes to so many N2s right there. Now, I'm going to do it for theoretical air. That means all of the O2 are used. There's no O2 in the products. There's no oxygen remaining in the products. It's perfect theoretical air. So now I have some coefficients. Did I put a coefficient in front of the fuel? I could, but did I? No. Here's recommendation number 1. Leave the number 1 in front of the fuel. Leave 1 in front of the fuel and don't touch it. Because a lot of things, what we'll do is write that equation per kilomole of the fuel, and then we'll use it per kilomole of the fuel. But now let's take a look. I want to balance this reaction equation. Here's the recipe. Here, rule just is leave the 1 in front of the fuel. The next one is balance the carbon. All right, well, if I left 1 in front of the fuel, and in the reactants, the only source of carbon is from the hydrocarbon fuel. So I look and I say, how many carbon are on the left-hand side of my reaction equation? 1. How many carbon do I need on the right-hand side for it to be balanced? If 1 is on the left, 1 needs to be on the right. So what is this coefficient right in front of the CO2 have to be to balance the carbon? 1. The second thing to do is balance the hydrogen. Same thing. You say, on the left-hand side, I have my hydrocarbon fuel and my air. Is there any hydrogen in the air? No. Where's the hydrogen? Only in the fuel. How many hydrogen are in the fuel? For this fuel, 4. I have 4 on the left. How many do I have to have on the right? 4. So I look. What is the number that I put in front of H2O? The only place I have hydrogen on the right. I need 2. You've now successfully balanced the hydrogen. The last is to balance the oxygen. Okay, to balance the oxygen, go backwards. Count up how many oxygen are on the right-hand side. Go slow here because this is very error prone. How many oxygen do I get from this part right here? 1 CO2. 2. How many do I get from 2 H2Os? 2. I add 2 and 2, and I go slow here because it's error prone. I get 4. All right, now that I have 4 on the right-hand side, how many do I have to have for balanced reaction equation on the left? 4. So what do I put right here? 2. Now the very, very last is the balance the nitrogen. Okay, let's balance the nitrogen. How many nitrogens do I have? I have 2 times 3.76. 7.52. So over here I have 7.52 N2s. True? This is 2 times 3.76 is 7.52. I can multiply by 2, but then over here I'll divide by 2 to get, because it stays N2. You're right. You have to do that a number of times by yourself. That's my balanced reaction equation. Those are the stoichiometric coefficients for the 100% theoretical air for the combustion of methane, burning of methane. What happens if I have excess air? What happens? Well, what I do is I rewrite my equation, forget the 1 in front of the CH4, I never write it, CH4 plus, and then I'll have 2 O2s plus 3.76 N2s. But let's say I have some excess air. How much excess air? Let's say 50% excess air. If I have 50% excess air, I put 1.5 right there. Let's say I have 30% excess air. Well, what coefficient would I put right there instead of 1.5? 30% excess air? 1.3. How about 70% excess air? What would you put? 1.7. You got the picture. See how you modify it for the excess air? What number do you want to run for this problem? 30%, 25%, 50%, 70%, 100% excess air? What do you want to run? 50%. So here's a 1.5. Okay. Now, when you come over here, does it change the stoichiometric coefficient in front of the CO2? By adding more air, did I change the amount of carbon on the left-hand side? So am I going to change the coefficient in front of the CO2? Nope, you will not. Leave a 1. How about the coefficient in front of the H2O? Okay, why would it change? Hydrogen, hydrogen, hydrogen dictated. The hydrogen balance dictated that one. Hydrogen only is in our fuel. So how it would not change. It would still be 2, true? Now, what is going to happen is you're going to have, let me bust it down here. You're going to have some excess oxygen that's going to be unused going out in the products. And you're going to have some nitrogen also, even more nitrogen that's going out, because it used to be you had 7.52 N2s coming in and you had 7.52 N2s going out. Can you tell what is this coefficient right here in front of the nitrogen? Can you tell from the nitrogen balance what that needs to be? It needs to be what? 1.5 or 3? Does it need to be 1.5 or 3? I'm asking a tough question because I don't want to see the error on the final exam. Is it 1.5? Well, does it really matter? Well, when you go and do the entropy calculations and the enthalpy calculations for the first law and the second law, yeah, it matters. You've got to get the coefficients correct. So this number right here is 1.5. Now it's a little bit of work to get the oxygen. All right. So how many people think they can work out that oxygen? I'm going to pause. I'm going to walk around. I'm going to see if you can work out that oxygen. All right. Well, this is a tough question. You have to work through it. I don't know how to explain it other than just redo the oxygen balance. And when you redo the oxygen balance, you're left with a 1 here, 1 O2s. Okay? Maybe I do it this way. How many oxygen do I have? Let's do an oxygen balance. How many oxygen balance do I have on the left-hand side in the products? I have 6. 4 times 1.5, 6. Okay. And then I come over here. How many do I have with the CO2? How many do I have with the H2O? And then I need some unknown A or X or something times 2. X is this. When you solve for X is 1 then. Okay? Makes sense? You just got to go back and balance it again for the oxygen. Okay. Now, what happens when I have deficient air? This is tricky. What's tricky? What do you mean by tricky? Well, that means you don't have enough oxygen to go around. And you're going to have to either be told what happens or some other information supplied, but it's not as easy. Because what happened to every one of the carbon when you had excess air? It went to CO2. All right. If you don't have enough air, maybe it tries to go to CO2, but some of it stops at CO. So it's going to be more difficult because you could have some carbon monoxide when you have deficient air. Okay? You're not likely to have a lot of it, but just enough will mess up your calculations. Okay? Or you could have just some CH4 go out, unburnt fuel. Just the fuel itself went out. Yes, sir.
So is that why we get carbon monoxide in a typical combustion engine? Because it's deficient air?
A lot of times it's the reaction didn't quite make it to everywhere in the whole chamber, combustion chamber. And so that's a reason that it's incomplete. But yeah, if you're running with a rich mixture, yes, your catalytic converters in there. Before they had catalytic converters, you're putting out hydrocarbon fuel. You could smell it, plus you don't want to breathe it because it would have some carbon monoxide in it. The carbon monoxide may not last long, but this is a thing of the past. Usually, it used to be if somebody wanted to commit suicide, don't do it. But they could just start up their engine and idle in a car in the garage, closed garage. Now all you'll do is wake up with an empty fuel tank and a little bit of headache. Thank you to the catalytic converters. So it's kind of idle all you want in your garage, but you're not going to die. The other thing is there's a lot of other emissions other than just carbon monoxide. That's the easy one to take care of in the emissions. That's the NOx, which are really the bad, which give you the ground level ozone from automobiles. In the summer, in August, we're about ready to see that in San Antonio. When you get up a little bit and you look down, you say, oh, all those poor people in San Antonio, what are they breathing? Ugh. Well, yeah, that's our exhaust, especially from emissions from automobiles and NOx. All right. A little digression there, but some fuel, unburnt fuel, or carbon monoxide when you have deficient air. But all you would do is rebalance the equation and resolve. Okay, air to fuel ratio. What is that? Well, it's just like it says, on a mass basis or molar basis. The air to fuel. Let me try and tuck it in over here. Erase this a little bit. The air to fuel on a molar basis is written with a bar over top. That's our syntax for this textbook for what a molar basis is. Now, it's the air to fuel ratio. So the number of moles of air divided by the number of moles of fuel. For this problem, 100% theoretical combustion of methane, how many moles of air did I have to complete? Go look at this reaction equation. It was 1 for the methane, right? How many moles? This is where we have error prone. If you go slow, right here. I don't give a lot of partial credit. Simple question. It's like, either you did it perfect or you didn't. You got 100% correct or you lost heavily. So how many moles of air for this reaction equation right here? Haven't heard the correct answer yet. Haven't heard the correct answer yet. I'm going to pause. I'm going to walk around because there's no sense me telling you. You've got to get the correct answer on the final exam. All right, so a number of people are coming in with 9.52. That's the number of moles of air. How do you calculate that? Well, you have 2 times the 1 for the oxygen plus 2 times 3.76 for the nitrogen, or 2 times 4.76 gives you the 9.52. A couple ways to calculate it, but you got to calculate it correctly. We didn't say how many moles of oxygen. No. It's the air to fuel ratio, not the oxygen to fuel ratio. And it's not the nitrogen to fuel ratio, it's the air to fuel ratio. Air is made up of oxygen and nitrogen. So there you go. How many moles of fuel came in for this balanced reaction equation? 1. So the Air-to-fuel ratio on a molar basis is 9.52. What about the air-to-fuel ratio on a mass basis? Leave the bar off, air-to-fuel. Would it be the mass of air divided by the mass of fuel? Sure. Would the mass of air, would it be the number of moles of air times the molar mass of air divided by the number of moles of the fuel times the molar mass of the fuel? Sure. Would that be my 9.52 times, what is the molar mass of air? Yeah, around 29, 28.97. Divide by, I have to get the molar mass of methane. 12 for the carbon, 1 for each of the hydrogen. 4 plus 12, it's around 16. I can look in the table and I find 16.04. 16.04. How many else? How many? You verify that? Good. Good. Okay. So then you just get your calculator, calculate that one. What does this air to fuel on a mass basis for 100% theoretical combustion of methane? What is it? Okay. Give me the first couple digits. 17.2. 17.2. That means I have to ingest 17.2 kilograms of air for every kilogram of fuel. That's the right mix, the air-to-fuel ratio. How many people at Gearheads work with automobiles know they could set the air-to-fuel ratio for their gasoline engine? What is it? Do you remember the number? It's like around 15, 14.7, 15, somewhere in there. Anyway, okay. What's that oxygen sensor telling us? They have a number of them right before and after the catalytic converter. The oxygen sensor is telling us how much excess oxygen's in our products coming out. That it's out after the header before you start to go to the catalytic converter, and then it usually has an O2 sensor there, and then they have one after the catalytic converter as well. Okay. All right, so that's air-to-fuel ratio. What about the fuel-to-air ratio? That F to A. You could do it on a molar basis or on a mass basis. Guess what? It's 1 over the air-to-fuel on a molar basis. It's 1 over the fuel-to-air. Whoops. 1 over the air-to-fuel on a mass basis. It's the reciprocal. That's all. The reciprocal. Ready to press forward? Propane combusts with air. Obtain a balanced reaction equation for complete combustion with the theoretical amount of air. Go slow. So we start with fuel, C3H8. Do I play around, or monkey around? Do I decide to change that coefficient in front of the fuel in my balanced reaction equation? Don't. Leave 1 in front of it, and even though you may be tempted to change it, don't do it. Don't do it. Just leave it like that. And now, where are we getting that oxygen from? Are we getting it from a bottle of pure oxygen, or are we getting it from air? That's how you get it from air. Where did this 3.76, Professor, come from? You just always write this 3.76 down. You could write it like this, 0.21 O2s plus 0.79 N2s. But they found it's a little easier to write 1 in front of the O2, and then you just have 3.76 in front of the N2. So it gives you the right balance of oxygen and nitrogen. All right, then it's going to go to CO2 and H2O. We also know that if it's going to be 100% theoretical air, then there's going to be no oxygen, and there'll be some N2. Okay, so I'm going to leave that oxygen, even though I know it's going to be 0 for part A. All right, let's balance the carbon. How many do I need right here for that carbon? Do I need 3? Does that balance the carbon? All right, what's the next one? Balance the hydrogen. How many do I need in front of the H? 4. Now the hard part, I go back and I get this coefficient in front of the O2, in parentheses with the 3.76 N2, by balancing the oxygen. So I count up. I go very slow. How many oxygen do I get from this one? How many do I get from that one? 4. I add them together, 10. Then I come back over here. Sometimes I'll write 10 over 2. Sometimes that math is too easy. I just say, I know what that is. It's 5. It's 5, okay? I got it. It's 5. Now, is the oxygen balanced? Yes. Then I come over here. If it's 100% theoretical air, there's no oxygen excess. And I have 5 times 3.76 N2. That's the answer for part A. Now it's complete combustion with 120% theoretical air. C3H8 plus 1.2 times 5 times O2 plus 3.76 N2. So I started with my 100% and I said I have 120%. So it's 1.2 or 20% excess air. That's my coefficient I put right there. Okay. Does it change the CO2? Does it change the H2O? But I'm going to have some oxygen left over. I'm going to have 0.2 times 5 oxygen left over. 100% of it was used, but 0.2, the 20% excess, was unused, and so it's the 0.2 times the 5 O2s. And then I'll have the 1.2 times 5 times 3.76 N2s. That's balanced for part B. Now the next question is part C. 90% of the propane consumed in the reaction with theoretical air. So let's go back to our reaction with theoretical air, and 90% of the propane is now consumed, meaning what happens to the 10%? Goes out with the products, So this is just trying to change it up. So let's start. We have C3H8 plus 5 O2s plus 3.76 N2s goes to. Now, I'm going to say that 0.1 times C3H8 goes out with the products. So what happened to the 90%? It was consumed. Where did it go? The carbon went to CO2 and the hydrogen went to H2O. Okay. So how many CO2s? How many H2Os? I have to rebalance the whole thing. Maybe I have some O2s left over, and I definitely have some N2s going along for the ride. Well, let's try our carbon balance. How many carbons? Let me try and do it up here, C balance. How many are on the left-hand side? 3. How many do I need on the right-hand side? Well, I'll have 0.3 from there plus this unknown X. So guess what X is? 2 point, what is it again? 2.7. Does that work? Is the carbon balance? All right. Then let's try the hydrogen balance. I have 8 equal to 0.8 plus X times 2. This is my X. So solve for X. And what do we get? I'm sorry? 2.6? 3.6. 3.6. Look good? All right. What about Now my oxygen balance, well, I'll have 2 times 2.7 plus 3.6 plus, didn't leave enough room, 2x. That's equal to 10. So what do we pick up? 0.5? 1 thumbs up? 2? 3? Good? All right. And then nitrogen, well, guess what? It's still going to be 5 times 3.76. It just goes for the ride. So is this the balance equation for part C? Okay, now part D, 90% of the propane consumed in reaction with 120% excess air. So you start with 120% excess air, C3H8 plus, oh boy, what is this, 6 times O2 plus 3.76 N2 goes to 0.1 times C3H8 plus some diminished amount of CO2 plus some diminished amount of H2O plus some excess oxygen plus some nitrogen. Okay, the nitrogen is 6 times 3.76. We're done with the nitrogen. But let's do the carbon. What is the coefficient that belongs right in front of that CO2 from a carbon balance? .7. And then what's the coefficient in front of the H2O? 3.6. True? But the oxygen's a little bit of work. So let's do the oxygen. So you have what do you get? We got a 1.5. And we're done. D. Make sense? Yes, sir.
The previous one, when we did the oxygen balance,
Right.
how come it's 10 not 5?
It's 5 times 2.
But isn't it on the right side? Isn't it an O2 also?
But it's 2 times x, and so we solve for the x. Right? But if I just look at this equation, it's 10 equal to 2 enter 2.7 times, which is 5.4 plus 3.6 plus 2x. And so x is a half. Make sense? I'm sorry?
12, yeah. It's supposed to be 1.42.
He's asking about part C. But when you move to part D, you have more oxygen on the left-hand side, so it starts with 12. That's when it ends up to be 1.5 for part D. Okay. Consider the complete combustion with 100% theoretical air, blah, blah, blah. Calculate the air-to-fuel ratio on a molar basis. Well, the air-to-fuel ratio on a molar basis with 100%, we just did the propane, true? How many moles of air to how many moles of fuel? You look back and tell me. That was the answer for part A on the previous page. 9.52. No, is it 9.52? It's 5 times 4.76, isn't it? Isn't that how many moles of air? Pardon? 23.8, right. So it's 23.8 divided by 1. So the air to fuel ratio on a molar basis, 23.8. What about the air to fuel on a mass basis? Well, I have to take and multiply the number of moles of air times the molar mass of air divided by the number of moles of fuel times the molar mass of fuel, or the air to fuel on a molar basis, molar mass of air over molar mass of fuel. So this would be 23.8, 28.97, and the molar mass of propane. I got to look it up. Something, I don't remember it. 24. Sorry? 44.09. There you go. And so we find the air to fuel on a, what did I do here? I'm doing it on a mass basis, no bar over top. It's 15.6. You can interpret that as kilograms of air per kilogram of fuel. Or just leave the units off. All right. Mole fraction of water in the products. That's important. It's going to be high. The mole fraction of vapor in the products. Well, it's the number of moles of H2O divided by the total number of moles of the products. Okay, well, I got to go back and take a look. What do you think? I have, let me calculate it here. The mole fraction of vapor for the reaction A would be I have 4 moles of vapor, and I have 3 of carbon dioxide, 4 of water vapor, nothing of oxygen, and I have, 3.76 times 18.8 of the nitrogen. So I add 7 to that, and I have 4 divided by 25.8. So it's a whopping 15.5% mole fraction. That's high. So that's why in cold winter days, if you look at the tailpipes of automobiles, I know we're not burning propane, but we're burning gasoline often. You'll see that white wispy stuff coming out. Well, that's because it's high vapor concentration, and when it hits the cold outside air, it condenses, and it looks like your little water droplets are forming. Just like when you walk outside and you blow your breath, right? And it's all white, cold winter day. Same thing, you're throwing out a lot of water vapor in your exhaust. Okay, in your breath. So this was 15.5%. And then what's that dew point temperature? Well, we want to find the saturation pressure for that dew point temperature is equal to the mole fraction of the vapor times the total gas pressure, atmospheric pressure. So the total is 0.155 for the mole fraction. And let's say 101.3 kPa. So it's 15.7 kilopascals. So at what temperature is the saturation pressure equal to 15.7 kilopascal? That's that dew point temperature. Somebody want to calculate that for me? Do you have your steam tables? around 55 degrees C. Close enough. All right? That's part E. This is part D. This is part whatever C. This is part B. And we already did on the previous page part A. I'm going to go ahead and stop this. Okay, one other thing we need to introduce here is a dry product analysis. A lot of times, water vapor, when you're in a laboratory and you're trying to analyze the combustion process inside the engine and you're analyzing what's going on in the exhaust products, that water vapor is a problem because it likes to condense. I mean, you get even relatively warm temperature, it's going to dew out on some equipment. So what they do is they often run the exhaust gases through something that dries it out. And then they have a dry products of combustion. So the dry product analysis is a molar analysis of all the products where they've removed the water vapor. So they removed it typically by condensation. It's just an added complexity to the calculation. All right. An engine burns with octane with 150% theoretical air. Determine balanced reaction equation. Dry product analysis will solve for part A and B. So let me go ahead and set it up. C8H18. We're going to get some unknown amount of oxygen from air. First, I'm going to do 100% theoretical air. Then I'm going to modify it for 150% theoretical air. Kind of two-step process. It goes to CO2. I can balance that carbon right away. It's 8. And it goes to H2O. I could balance that hydrogen right away. It's 9. This is where I go slow. This is 16. This is 9. I add it together, it's 25. So when I come back, I can put 25 divided by 2. And that will be my theoretical, 100% theoretical air. Okay. And then to wrap it up, I'll have my 25 divided by 2 times 3.76 N2. Okay. So there it is. It's not my balanced reaction equation for the problem. It's not the answer to part A, but it's a step toward it. Now I rewrite that, CH818, and now I'm going to have 1.5 times 25 over 2, O2 plus 3.76 N2. So there, now I have too much air. I have 50% excess air. We still have 8 CO2s, 9 H2Os, and I'm going to have some unburned oxygen. Well, it's going to be 0.5 because 1 of that was used. 0.5 is the excess. 25 over 2 O2s plus how much nitrogen? 1.5 times 25 over 2 times 3.76 N2. And there's my answer for part A. See how we did that? I went slow when we introduced it, but I think that's, you could follow that, I hope. Now, what is the dry product analysis? What are we asking for? The mole fraction of the carbon dioxide, mole fraction of the oxygen, and the mole fraction of the nitrogen in the products when there's no water vapor in the products. So, maybe I write it out that the dry products will be 8 CO2s plus, this is 12.5, half of 12.5. It'll be 6.25 oxygen, and then 70.5 N2s. At some point, it's nice to work with these multipliers, and then some points just put the number all and put it 70.5. And so when we add it up, we have a total number of products. So 70.5 plus 6.25 plus 8. So it gives us a 84.75. So the mole fraction of CO2 is 8 divided by 84.75. So the mole fraction of carbon dioxide is 9.44%. Mole fraction of oxygen is 7.38%, and the mole fraction of nitrogen, dry product analysis, is 83.2%. That's answer to part B. We could then say, what is the mole fraction of water in the products? Well, go back, we already did that. It's going to be 9 divided by 84.75 plus 9. You can make that calculation for part C. Do you want to solve for part D? What is the amount of water produced in kilomoles per kilomole of fuel? Sure. You're going to have 9 kilomoles of water per kilomole of fuel. That's the answer for part D. So how would I write that? Number of moles of vapor per number of moles of fuel is equal to 9. Answer part D. All right. What about part E? Amount of carbon dioxide produced in kilograms per kilogram of fuel. I need a little more room to do that. I'm going to scoot down just a little bit for part E. So this is going to be the mass of the CO2 per mass of the fuel. True. That's going to be the number of moles of CO2 times the molar mass of CO2 divided by the number of moles of fuel times the molar mass of the fuel. Okay. How many moles of CO2 is there? 8 per 1 of the fuel. The molar mass of carbon dioxide is around 44. I forget the exact change on it. And the molar mass of the fuel, octane, oh boy. Let's just say 8 times 12 and add 18, around 114. And so the mass of carbon dioxide per mass of fuel is 3.09. Kilograms of CO2 are produced per kilogram of the fuel. That number seems unreasonable. It's like, hold it. If I burn 1 kilogram of the fuel, I get more than 1 kilogram of carbon dioxide out? I get 3 kilograms of carbon dioxide out? Dioxide's a little 12 on the carbon, and how many O's are there? 16 and 16, there's 32 on the O's. So it's really heavy in the oxygen. CO2 is heavy in the oxygen. So you get, where did oxygen came from? Air. So anyway, you're right. It's 3.09 kilograms of carbon dioxide per kilogram of fuel that's burned. Okay, I'm going to give this one up. There's more problems. Let's talk now about conservation of energy for a reaction system. This is the generic fuel. CAHB. Syntax used in the textbook, so I try to stay with it. And you bring in some air, oxygen with nitrogen, and you want to go out with carbon dioxide, you want to go out with water, and you want to go out with nitrogen. When you have that, it's balanced. It's 100% theoretical air, is it not? So what is the excess? Nothing. One thing is, notice, the nitrogen comes in, the nitrogen goes out. Is it the same amount? The nitrogen didn't participate in the reaction, did it? So guess what? It's on both sides and with the equal stoichiometric coefficient in our balanced reaction equation. But one thing, typically, when you have a reacting system, and this is combustion, these all come in relatively cool. What about going out? Relatively hot. So energy-wise, that nitrogen is very important because it was heated up as it went through the system. And it took energy to heat it up. Where did energy come from? By breaking and changing those chemical bonds in the molecules. So if I said apply conservation of energy, you'd say at least I'm going to draw a control volume. I'll look for partial credit, right? Conservation of energy, I better write a control volume. And it looks like I have flow in and flow out of the control volume, right? So maybe I start and I say the most general form of the conservation of energy equation for a control volume is the rate of change of energy in that control volume with respect to time is equal to the rate at which it flows in with heat minus the rate it flows out with shaft work plus the rate it flows in with some enthalpy and kinetic energy and potential energy. These are all coming in. And then we have the mass flow rates times the enthalpy and the kinetic energy and the potential energy all flowing out. Does that equation make you happy? Does it look real familiar? Sure, I hope so. Now, we would say to ourselves, if you just have a reacting system, do you think it's running steady state? Sure. Very rarely do we have a true transient problem, even for a simple conservation of energy equation. It's just most application problems analyze steady state. All right, any shaft work. Well, you could, but most of the time is zero. Okay. Well, what about kinetic and potential energy? Often they're negligible. So changes in kinetic and changes in potential energy are negligible. And so what we have is we have that the rate of heat transfer in, but you know, if it's a reacting system, it's going to be a negative in, but we'll still leave it kind of Q dot in is equal to the sum over all that's going out. That's all the products. The mass flow rates times the enthalpy of what? All of the products that are exiting minus the sum, that's a bad looking sum over all the reactants. The mass flow rate times the enthalpy coming in. At this point, we would stop, we would say, this is great. I need to get the enthalpy of things like the carbon dioxide, the water vapor, the nitrogen is hot, reactants, I need the fuel, CaH8, CaHB, the oxygen, and the nitrogen. It's like, hold it, the same amount of nitrogen came in and went out, but we have rearranged the oxygen. It used to come in O2, now it's going out CO2 and H2O. We have to go back and look at how do I evaluate these enthalpies. Well, you could also write this on a molar basis. You could write, instead of a mass flow rate, you could write it as the sum of the molar flow rates times the molar enthalpies of all the products minus the sum over all the reactants. The molar flow rate times the molar enthalpy of all of those reactants. All right, the one other little step that I left out, let me do it right now. We'll do Q dot in divided by the molar flow rate of the fuel. So we'll put everything on a molar flow rate of the fuel basis. That will give us the sum over all the products. And then there'll be an N without an N dot. H bar for all the products minus the sum of N without a dot H bar for all of the reactants. What is this N right here? What are those N's? Those N's are the ratios of the molar flow rates divided by the molar flow rate of the fuel. It's the stoichiometric coefficient in our reaction equation, where we left the 1 in front of the fuel. Okay? All right. Well, I need to calculate those enthalpies. So what we have is we want to calculate the enthalpy of, let's say, carbon dioxide. The way you calculate the enthalpy of the carbon dioxide on a molar basis is get the molar enthalpy of formation of that carbon dioxide and then evaluate the change in the enthalpy from the reference condition where it was evaluated, 298 Kelvin, to whatever temperature that we're interested in. So it's like a constant plus a delta H. That delta H, if you want to calculate the molar enthalpy of CO2 at 298, well, this delta H is 0. If you wanted to calculate at 500 Kelvin or 900 Kelvin, then you have a significant delta H here. Okay. I didn't write that equation too cleanly. Let me write it again. The enthalpy of formation, the enthalpy on a molar basis of something like carbon dioxide is equal to the enthalpy of formation of the carbon dioxide plus some delta H bar of the carbon dioxide. That delta H bar is from the reference condition 298. So what is this term right here? This molar enthalpy of formation. Well, it's listed in a table 825. Table 825 has a bunch of substances, carbon, hydrogen, nitrogen, oxygen, gives us the formula. Carbon, look at that, it's C parenthesis S. What do you think that parenthesis S stands for? Well, right here they have parenthesis G, and down here they have parenthesis L. What do you think the parenthesis S, G, and L stand for? Solid, gas, liquid. That's exactly right. Okay, so when they talk about this oxygen, they're talking about O2 in the gaseous state. Okay, its molar mass. Hey, that information's repeated in some other tables for a lot of the elements in this table, but not for all of them. Notice they emphasize kilograms per kilomole. That looks good. But here's the enthalpy of formation. Look at the syntax. It's H bar per molar amount, so it's kilojoules per kilogram. It's of formation at our standard condition. What's standard condition? Think 298. Think 298. Reference 298. How hot is that in degrees C? 25. How hot is that in degrees F? 77. It's our high temperature of today. Would you like a high temperature of about 77 today? Or do you think it's going to be 100 today? It's going to be 100 today. That's what it is. It's going to be hot. So this is standard temperature in chemistry and physics, average temperature based on the Earth. So now that we have this is the enthalpy of formation, let's take a look at some of them. Let's look at oxygen in a gaseous state. What's its enthalpy of formation? 0. So some values can have an enthalpy of formation of 0. Basically, oxygen or some of the other ones like nitrogen and hydrogen and carbon, they set them to 0 because that's the predominant way they're found by themselves in the atmosphere. Kind of like a dead state, but we wouldn't use that term. But you're right. Now, carbon monoxide and carbon dioxide. Well, this is negative, a large negative. So as you start to get more complex molecules like carbon plus oxygen, well, then you're starting to deviate from that reference condition for those elements. And notice this is a negative and that's a negative, true? Little confusing, but you need the negatives. Otherwise, you have sign errors. And just chemistry is full of these negatives, and this chapter is full of negatives. Okay. Mechanical engineers, probably would have straightened that all out. We'd have had positives. But, sorry, when it's an exothermic reaction, it's heat out, it's a negative. Okay. Now, take a look down here. What do I have for water? I have 2 rows for water. H2O and H2O. Okay. What is G and L? At about 77 degrees F, I can have a cup of liquid water. I could have water in the vapor phase. At 25 degrees C, room temperature, I could have water in a liquid, water in a vapor state. So they have the same molar mass, but they have a different enthalpy of formation. It's related to the heat of vaporization. Here's methane. That's a good fuel. Hydrocarbon, CH4 gas. There's its enthalpy of formation. Here's propane, another fuel. Here's octane. Didn't we say octane was like gasoline? And you can get it in the liquid state as well as the gaseous state at 25 degrees C. You could have a cup liquid octane, like you're pouring fuel into your gas tank, as well as you could have it vaporized and going into your internal combustion engine at around 25 degrees C. So there are the 2 values. Let's start to compare these values. Let's throw out on this scale right here, let's put 0. Okay. Let's put negative 100, negative 200, negative 300, negative 400. And these are in 1,000, 10 to the 3, kilojoules per kilomole. Or if you don't like the 10 to the 3, take that off and put 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. Let's put in some values. Where is oxygen? Right there. And that's in the gaseous state. Where is the carbon in the solid state? That's like coal. I know coal isn't pure carbon, but it's like coal. How about the nitrogen in the gaseous state? There it is, all at zeros. Let's take a look and put another value up there. Where is methane, CH4, negative 75,000. Okay, well, that's right around here. CH4 in the gaseous state. Pick another one, propane. Propane, negative 104. Right around right there. C3H8 in the gaseous state. Let's pick another one. How about the 2 other fuels, the octane? The octane is negative 208 for the CH818 in the gaseous, and then about negative 250 right here, CaH18 in the liquid state. Let's put some other ones on. How about some products of combustion? Where does all the carbon in our hydrocarbon fuel, where does it go into the products? It goes into CO2, carbon dioxide. Where's carbon dioxide? Negative 393,500. So its carbon dioxide is CO2 in the gaseous state. What about the water? Let's say it goes into water vapor. That's around 285. That's, come on now, right out. H2O in the gaseous state. There's not a lot of insight I can help you with on these numbers other than showing that they're all negative except for the ones at 0. There's a positive 1 or 2 around, but you have to look. And what happens is as you go from some of these fuels to break them down, they're going down to the carbon dioxide and the water. So it'll make our reaction equations work. We'll calculate negative Q's. Because what was our reaction equation for CH4? CH4. It went to 1 CO2 and 2 H2Os. How about C3H8? it goes to 3 CO2s and 4 H2Os. So you're getting multiple CO2s and multiple H2Os for each of the fuel. Okay. So this is our balanced reaction equation. Often we don't have any shaft work. Often it's exothermic, a large negative Q dot. And you have to calculate the enthalpy of each of the components of the products. Start with the enthalpy of formation and then see if it's hot or cold compared to 298. Same with the reactants. Enthalpy of formation, then see if it's hot or cold. You need to adjust it compared to 298. Often, the fuels in the reactants, like the oxygen, often are at 298. So the delta H bars are 0. Often, but not always. Often. Okay? So what happens, some cases, you'll bring in your reactants at 25 degrees C, and you'll take out your products. Now, this is a positive Q dot, true? If these products go out as hot as it can go out, then this is 0, and this is the temperature, the adiabatic flame temperature. We'll talk about that in a minute. There's no heat transfer from the combustion away. That would be the hottest the products go out, the adiabatic flame temperature. The next extreme would be, hey, they come in at 25 degrees C. They go out at 25 degrees C. This is very, very hot, right? Very hot. Well, if the products went in at 25 C, I had combustion, I'm burning methane, and yet, reactants in at 25 C, the products out at 25 C. Tell me a little bit about Q dot. Large negative. Large negative amount. Okay? You're getting the most heat transfer out of that combustion chamber in that case. All right. I don't know why I'm going slower than I thought I would. I don't think I have time to solve this problem. So I'm going to have to stop, and we'll pick up there next time because I have to turn back the exam and go over the exam, okay? Let's do that. So I'll go ahead and stop.